Hi, welcome back to video tutorial on AIOS. In this video, we'll be discussing a very important concept, AIOS block scaling and load testing. And in this video, we'll be discussing the strategies behind load testing and policies and metrics system that will be used to do the block scaling. We'll be discussing this video. And this notebook provides an overview of block scaling and load testing of blocks in AIOS platform. This tutorial is designed to help users to scale the blocks based on the varying demand and also to monitor the blocks by their metrics using metric system provided in the iOS. So first we'll discuss what is scaling. So scaling is a process of adjusting number of instances of block to meet the changing demand of or a workload requirement. Let's say you have a sudden burst of input requests coming in, and how to scale those blocks, or now demand is going slowly down, how to bring down the scales or the instances so that you don't incur too much of hardware, or you can relieve the hardware for some other tasks. So that's what is about the scaling. So scaling can be done manually or automatically based on the predefined policies or rules. Manually, you need to hit certain APIs to do manually, which I have already given an intro on reassigning the blocks. And automatically is what we need to create the certain policies. So right now we have written certain policies for taking the scaling up and down, and which you can take as a base, and you can also modify those policies. Scaling of instances across nodes of a same cluster is supported in AIOS. Right now, within across the clusters is not supported. Within the cluster only, will be able to do a scaling. And to do the scaling, we'll be using block policy concept. And what all policies will be used is resource allocation policy, which is used for allocating the resource. Identifying which is the proper node, proper GPU for my model. That's what will happen in the resource allocation. Load balancer policy, where this policy will determine which instances coming request has to be routed. And auto scaling, so basically to identify there is a bottleneck in the available instances and I need to scale it or upscale or downscale. That decision has to be taken by autoscaler policy. And a health check policy, this is basically used to monitor the running instances, and if something is going wrong with the instance, then bring that reassign that instance down, or notify any, like the admin maybe to take the manual control. So this is about scaling. So let's go with the resource allocation policy. So the code is accessible here. So this policy defines where the block instances should be deployed within the cluster. Let's say you have a number of nodes. First of all, we need to select the good node for this particular model, and as well as in that node there can be several GPUs. Since I'm deploying an AI model, I require a GPU, and which GPU to choose, whether it is a single GPU or whether should I need to use a multiple GPUs. So those things can be defined in this resource allocation policy, and it can include rules based on block resource requirement and nodes resource availability. So any AI model will have its own requirement, like say it requires some amount of GPU RAM, CPU RAM, storage, etc. So that is a block resource requirement. And node resource availability, so you have a number of nodes. In that, certain nodes might be already burdened with certain tasks, or it might not have enough RAM, or it might not have enough storage. So such kind of checks you need to do before allocating an instance in a node. So just to give certain examples, deploy instance on a node with at least 4 CPU and 8 GB RAM. If this is the requirement of a block, then we need to identify such node where this is available. Or just to give an example, deploy instance on a node with at least 1 GPU is required, and it has to have a 35 GB RAM available. So this is the requirement of a block. Avoid nodes with less than 20% of a vCPU available. So this is you are understanding the node resource availability. You are trying to avoid, you are not going to take that node for a deployment. So deploy instance on a node with 1 GPU with 35 GB RAM available, and or 2 GPU with 16 GB RAM available in each. So this is where a model can run in 2 GPUs as well, or a model will run can run in a single GPU. So this is where the resource allocation policy comes into picture. So we have discussed in certain videos how the resource allocation policy looks like. So the code that I have shared here is, I'll just walk you through the code. The function.py is the main file here, and rest all are the registration files and uploading files. So basically you have a file, and you need to zip that file and upload the zipped file using that upload.sh, and you need to register, like say this, since this is a policy which will be getting going to run in AIOS system, you need to have what is its input, what is its output, what is its the parameters or settings. So for all those details, you need to fill that in the registration JSON, and then you can do a registration. So how to do all those things are available in the Jupyter notebook once we go in. But I'll just show you the code of maybe this function.py. So this function.py has one is init function, one is eval function. In the eval function, you have some if and else conditions. So this third party allocate is for mainly for this we have discussed in one of our video, where you want to split the model using some third party libraries. So during that time, how to do it, so that's where this will come into picture. Apart from that, we have dry run as well as allocation and scaling, action equal to scale or action equal to reassignment. So this based on this actions, right? So it will, we are calling individual functions. So this reassignment policy we have already discussed in one of our video, where it identifies there is an health system which will run along with this resource allocation along with the load balancer. So that health system subsystem is responsible for monitoring the instance and identify whether the instance is healthy or not. So based on rules set, so if it identifies that it is not healthy, then you can call this action equal to reassignment via REST API, and then this unit will identify which is the other node, I mean which is the better node for running this instance again. So it will identify that node and it will run, it will assign a new instance to that particular node. So this is where the self-handled reassignment function is called, and whatever it returns will be passed on to the AIOS, and AIOS will deploy that particular instance in the given GPU node and node name and GPU ID. So and allocation, right now this allocation is used for first time allocating the instances, like say whenever there is not even a single instance is available, first time if you have to deploy an instance, so the allocation is called. And hereafter, anytime if more instances of the block is required or a lesser instance of block is required, then a scale function is called. So let's this dry run is for just for a dry running, it will not do a resource allocation, it will just evaluate what could be the score of a dry run. So it has to provide some node information, like which node it has chosen and which node which GPU it has chosen. So basically it has to end at the end, it has to send only the score only, just to say okay, dry run is in this node is okay. So let's see the handle allocation and handle scale. So handle allocation function is here. So what this does is basically just extracts the resource requirement of a block. So block we would have given maybe like okay, this instance might be requiring this much of CPU, this much of RAM, this much of storage, or this could be it requires this much of GPU or GPU RAM. Certain informations of the block would have been given either during the registration time or maybe when you are running the block itself. So that details are gathered here from this extract resource information. I'll not go in detail like what all things it is doing. Maybe you can have a look at it. And next is a get available node. So you have a cluster and cluster metrics, right? And also the healthy nodes also is provided by AIOS to you. So in that, which is the node, what are the nodes are available for me? So that's what we are fetching it here. And next, look, this function is called, this is the main function which is used by all other functions, orchestrate allocation helper. Even in handle scale it will be the same. You are trying to extract the resource, get available node, and you are calling the orchestrate allocation helper. And even in case of reassignment also similar, where only in the reassignment you will get extra information like what instance ID to reassign, and what is the pod name of that instance ID. Each those details also you will get in the reassignment, but not in the scale or allocation. So there also you will do the similar check, and also you will try to avoid the same like let's say one node is having some issues and in that the pod was running, so that we have identified. So I just want to avoid that node. So that's what this get current placement will do. So where is the current block ID or instance ID is running is what will be checked, and with that information we are passing that to later stage in this. So we are trying to avoid that particular current placement node using these conditions, so that those nodes will not go into the allocation. And then again we are calling the orchestrate allocation helper. So this is the main function that we have to check. So in this resource allocation helper, first it identifies eligible GPU. So you have another function which will take the available nodes and the requirement of the block, and based on that it will try to identify GPU eligible nodes, and that will be the input to the next function call, which is a score CPU memory. Now GPU memory is over. We are not explicitly checking the GPU utilization right now, just for the sake of simplicity. And maybe you can add that also in this particular place, where you can monitor the not just the GPU RAM, you can monitor the GPU utility as well. Next, whatever the RAM wise, whatever the GPUs nodes are available, right? So that will go as an input to the next. It's basically ANDing operation. Output of one is fed to the input of the other function. So you are trying to score the CPU memory based on the CPU memory, whatever is eligible, right, available. So that will you will get in memory eligible nodes, and again this output will be fed back to again one other function, score CPU. So CPU also needs to be checked, not just the memory. If something is not available, right, then and there we are returning like error and GPU. This error will be passed on back to the AIOS, and the AIOS system will understand that okay, resource allocation is not possible, and it will not do a resource allocation. So here also we are returning if there is no GPU eligible nodes. And then again CPUs will be checked. So basically vCPUs or whatever the requirement is there, right, it will be checked, and if it is not available, it will return error, or if it is available, we have to we'll send this output to the next, where the storage check will happen. So storage check is also has to be done, because LLMs can vary from 1 GB to 100 GBs, right? So storage is also very important. So once the storage eligible nodes are done, you will calculate a weighted score for all the nodes. Let's say at the end of the storage eligible nodes, right, I have 5 nodes, meaning these 5 nodes are eligible from all other functions. So those 5 nodes, in that 5 node I need to choose one node. So for that I'm doing a weighted average. I'll get a calculate weighted score will be called, and in that I'm passing all the scores from individual functions, and that will be composite score is created and is returned back, and in that maybe the maximum one only I'm taking, and what is that node and what is that GPU I'm finding, what is that GPU and what is that node is what I'm sorry, what is that node ID is what I'm taking here, and that with that node ID I'm sending it back to allocate GPU IDs. So once that node ID is sent, in that node only right now the requirement is checked again, whether let's say if multiple GPUs are available in that node, what GPU to select will be chosen in this function, and finally it will allocate a GPU. So that will have a basically GPU ID. So one important thing is, let's say if one as I've given in one example, right? So if one if let's say this is the requirement, either 1 GPU with 35 GB or 2 GPU with 16 GB RAM on each, then this will take care of that as well. Let's say if GPU is an array, if only one GPU is available, first of all it will try to prioritize first single GPUs, then it will try to prioritize sharing of GPUs. So I can show you that function. Yes, allocate GPU IDs. Sorry, it happens just before. Let me just go to available GPUs. Handle allocation, extract resources, get available nodes, orchestrate. Okay, just give me a minute. Yes, so this is the function. Score GPU memory is the function where first check will happen if single GPUs are available. Check if any single GPU has enough memory for the current requirement. If it is available, then that GPU is chosen, and we are not going to run the else part. So basically if this we are not at all getting even single GPU from any node, right, then we are going to check this if condition, where if no nodes found with single GPU, try multi GPU pooling. So it all depends on what library you use. Let's say a library that you are using doesn't allow model being splitted, so then you need to comment this out, because a single library that you are using is not allowing you to split the model across two GPUs in a same node. So right now I'm using a VLLM, so that will allow me to run the models across the GPUs. So that's why I'm having a multi GPU pooling also will be taken care. So multi GPU, so the strategy here is 2 raised to n GPUs you need to select. Let's say you have 7 GPUs. So in that, if one GPU is not enough, then you have to choose next is a 2 GPU, next is a 4 GPU, next is 8. 8 is not available because only 7 GPUs are available. So 8 is not possible. Either you have to use 2 GPUs or you have to use 4 GPUs. So first it will go to 2 GPUs. If 2 GPUs are available, then fine, it will choose that. If not, it will again loop it to the next GPU count, which is like 4. So if 4 is available, then great. So it will allocate that GPUs. If not, it will not. It will come out of the for loop. So there is a loop here, right? So it will come out of the for loop, and it will say no, that is also not possible. So with that, we'll get to know whether it's a single GPU allocation strategy or multiple GPU allocation strategy based on this the last function that I was showing, right? Allocate GPU IDs. It will take a call of identifying which is the GPU, which is the GPU. Whether if it is a single allocation strategy, it will choose one GPU, and which has enough RAM for this. The biggest, maybe like it is sorting out the biggest RAM available. Let's say you have 4 GPUs. In that, 2 has a good amount of GPU, but 2 doesn't have a GPU. So once the sorting is done, whichever is having highest will be given for a allocation. If it is a multi-GPU strategy, it will try to sort it, and it will try to check whether the free memory is available in each GPU when you sum up is sufficient enough for this particular model or not. With the buffer as well, buffer also will be added. So this is the whole resource allocation. So to understand certain parameters of this policy, right? So I'll just go through this particular Jupyter notebook where it has some parameters like minimum CPU per instance. Minimum, what this means is to run this instance, you require minimum of X number of vCPUs. So that's what this instance is. This is the information that we are passing on to our policy, and policy will use these informations to identify the resources requirement, how much CPU, GPU, RAM, storage is required for this particular instance to run is what calculated. So this is the number that we have to pass. Similarly, minimum memory per instance, what is the CPU RAM is required, that's what we need to mention here in MB. Minimum GPU memory per instance, so GPU memory, how much is required in MB is we need to mention it. Minimum storage required, because the files will be stored at static, right? It will be, files will be stored, downloaded and stored in the instance, so minimum storage is required. And GPU memory buffer, so to calculate, let's say you have made some mistake in the measuring the GPU RAM requirement, so then you can add some buffer to it. And the node thresholds, let's say you don't want to choose a node which is having CPUs, let's say 80% CPU's occupancy is over, then you don't want to choose that node. So in such cases, you can use this threshold. Similarly, memory threshold and storage thresholds are also available. And also to calculate composite score, we had on weights. So what is the weight you want to strategize? So here GPU memory is taking 45% and rest all taking like 25 to, so summing up to 100%. So this is the weights I'm using. I'm giving a higher priority to the GPU memory. So if GPU memory is not available, since it is taking a priority, so GPU memory is taking a higher priority here, as we are giving a bigger number. So sample, I'll explain it later. So this is about the resource allocation. So next is a load balancer. So load balancer job is to identify incoming requests. If in that every request will have its own session IDs. So session ID, if it is not already routed to some instance, then it has to identify which instance it has to route. So it has some its own policies, rules. You can modify accordingly your need. So this load balancer identifies which instance is having maybe a minimum load or not much of task coming to this instance. So it will try to adjust based on the parameters you set. So code is available here. So let it load. So this manages the distribution of incoming requests across the blocks instances. So there might be several instances, which instances to choose will be decided here. And once it is decided, so whenever again one more request comes from the session ID, again it will not decide because this decision is already taken in the previous iteration. So it will simply pass on that information. So only during the decision time it might take some extra compute. Once it is decided, they'll be very quick, so they will not take any other compute at all. And also there is one other thing, we call it as redistribution. Let's say uh, for some reason if the number of requests that you are sending is queued for some instance, and maybe one or few instances having lesser queues, then we have to redistribute it such that all the instances take on an average, they take almost same request. So for that reason we call it as redistribution. So that also will be taken care here in the load balancer policy. It can include rules for session persistence, request routing, etc. Example, route all requests from a specific user to a same instance. So it's up to you, like what you want to strategize, or you want to make it a generic or something like that, hard coded. All those details you can parameterize it. So route all requests from a specific user session to a same instance. Distribute request evenly across all the instances. These are certain rules that you can think of. Route request based on the geographic location of the user. So such kind of things also you can do it here. Route request based on the type of request. Let's say it could be an the chat request. It could be a burst of kind of simply generating a tokens, not like a chat kind of interface. So such kind of things also you can identify and you can route. So to I'll not in detail related to the code, so you can just go to the code, and again there is a function.py. You can understand it has an eval function. In the eval function we'll be doing certain operations based on the uh, it's like it might take more time for me to explain, so that's why I'm avoiding explaining this. But what I'll explain is the parameters. So let's say this is a load balancer parameter. So it has a selection mode where two values are possible, weighted and equal. Weighted, it does some weighting activity. Later on I'll explain that. And equal is basically choose a instance with the shortest queue length, so that when a shortest, the queue length here is basically every instances, right? They will have their own queues. uh, Basically the load balancer, once it assigns, the task will go to the queue, and the instance will pick the data from that queue, and it will try processing it, and it will return the result back. So that's what we call it as queue. So based on the shortest queue length, the task will be switched in the equal mode, whereas in the weighted it will do some weighted activity with certain parameters. So right now in our current experiment we have used this equal, and basically it will try to manage equal number of requests going to each instances. So weights of a different metrics. So it must sum to 1. So right now we have session id based, and queue length based as well, and a latency based, or requested tokens per second. So these are the four parameters available, but it prioritizes only these three: active sessions, queue length, and latency. So you can add more number of kind of parameters to it. Maybe if in case you want to geography based or something like that, you want to add, right? So you can add those details as well. So here active sessions, number of sessions in a instance will be weighted with 30%, and queue length is taking higher priority or precedence here 40%, and latency is taking 30%. This is the meaning of this particular dictionary. So weights are, if we are selecting a weighted, then these are the weights it will choose. If it is equal, this will be of no use, so it will not be using the weights. Since it is equal, it will give it to the shortest queue length instance. So averaging period. So for any task you want to average it. Let's say you have a load balance. It's like similar to Linux, right? In the utility or system load, when you are monitoring, you have 1 minute average, 5 minute average, or 15-minute average. So similarly, we have here average 1 minute or average 5 minutes. So you can choose any of those two values. Basically, it is used for averaging of the queue lengths, or averaging of any. It could be queue length, or it could be sessions, or anything. So tiebreaker policy. Let's say when you are selecting, you identify two instances. I need to choose. So why have a two is because of the score that it has calculated. So score is being calculated, and they are found to be same. Then which one I have to choose? So whether it is first instance created, like when you are creating instance, there will be a first instance, right? Whether you have to choose that, or a round robin. So round robin is chosen, so that evenly we are making sure that the request will be routed to all the instances. So next, metrics configuration. So what this metric configuration is, basically there is a max threshold for queue length and active sessions, right? So this is just to bring the maximum values. Since we are bringing we are whatever the queue lengths we have. Let's say we have 5 instances. It has a one queue has one has a queue length, and one has 1,000. So to bring them in proper scale within 0 to 1, we whatever beyond that 500 is there, right? So we are just making it as a 500. We are not going to take that 1,000. So whomsoever are beyond 500 will be treated as 500, and whomsoever below 500 will be retain their number, so that we will calculate some normalizing the queue lengths. So once yeah, this is for the normalizing basically. So this invert score is just to invert the score, so that if invert score is true, it means lower value are better, so higher is the score. So this is the metrics configuration. Next is session management, session timeout seconds. So how long to keep a session cached before cleanup? Let's say I'm creating a session, I'm creating a new chat now, and I'm chatting it, and I have sent some request, and if I'm not chatting again, let's say within 1 hour or something, so there's no need of maintaining that session in my load balancer, so that I can clean up of sessions can be done, or else it will be like too much of sessions I need to hold in my load balancer, right? So I can clean up those sessions which are not active right now. So that's what this timeout will do. And redistribution of parameters. So I was saying, right, so periodically we'll be have to do redistribution as well, so that the queue length should not be skewed, or the request should not be routed only to certain instances. We need to be keep a redistribution in the backup, back as a behind, whether the hits will come to that instance or not. You need to keep redistributing the dictionary or the memory state variable that you are holding. So the redistribution interval is mentioned here. So by default it's 5 minutes or 10 minutes. Once you can, if this is 600, it means 10 minutes, basically 600 seconds you need to do redistribution. So task imbalance threshold. So it's a fallback actually. So what we are doing is we are trying to get the metrics from each instances. So if in case we are, because of some issues, if we failed to get the metrics, right, so block metrics is not coming to the load balancer, then this acts as a fallback. So what it does is basically redistribute if one instance has a 50 more tasks than others. Let's say any it will identify uh, average queue length based on the average 1M or average 5M. If any guy is more than 50%, 50, if any instance having queue length which is more than the average, right? So more than by this number 50, more than 50, then it will do a imbalance. I mean, it will try to do the redistribution. Then redistribution percentage. So how much you need to redistribute here? So basically it will try to redistribute. Let's say if this is 0.5 is the value, 50% of the session when a new instance are added or anything, right? So let's say there was one instance which was having like 5 sessions. In that 5 sessions you have 30 requests, and a new instance has been added, and now routing has to be done there. So to do that, let's say now there is no new hits are coming, no new session IDs are created, but it is the same session IDs which are keep on hitting, then this new instance will never get a hit at all. So during that, during the redistribution, I need to send some instance to the new instance created, right? So for that reason, the 50% of the session, let's say we have 6 sessions in the instance 1, 0 sessions in the instance 2, then 50% of the sessions will be taken from the instance 1 to given to the instance 2. That's what this redistribution percentage is. And redistribution interval I have told already. So redistribution selection mode. So how to select instances for a redistribution? So whether it is a least loaded method or a random method or a best method. So here it is a random method, randomly assign session during the redistribution. You have multiple instances, right? So let's say multiple instance has been identified to select. Let's say you have multiple instance has been identified which needs a redistribution. Let's say out of 6 instances, 2 instances are having skewed queue length, so their queue length is very high. Now you need to redistribute them. Which I need to choose is what will be redistribution selection mode will decide. So imbalance threshold, minimum difference in queue length is needed before redistribution. So what this means is, if this condition is not met, no redistribution will occur. This is to avoid small fluctuations causing unnecessary redistribution. So what this number is, minimum of 5, let's say example is 5, minimum of 5 has to be there for me to take a decision on whether I need to redistribute or not. If this is not there, right? So I mean, it is compared to the average. If the 5 plus or minus is not there than the average, then I'll not take this for a redistribution. So it could be like a small skew only, it's not a big skew. So only one big skew is there, then only I need to consider. Let's say newly one instance is created and it is getting only one session request, and the request numbers are very less, right? So I should not take an immediate decision on whether to redistribute or not, since it's very small only. And overloaded threshold percentage considered Basically, to identify which instances are overloaded, this percentage is used. So you have multiple, you require one parameter, right? So you require one scale to say whether this instance is overloaded or not. So that is what the 50% of the above the average. Let's say your average queue length is 100, and if any instance is having more than 150, right? So that uh, block is considered for a overloaded. And if multiple blocks are there, what to choose is will be chosen here. But first of all, to take a decision whether to redistribute or not will be taken by this guy, overload threshold percentage. If any instance average length is more than 50% of the average, then that will be then redistribution is kicks off. And to which one to choose the redistribution, let's say if multiple instances are having more than 150, then this will be used to select that particular instance. And for performance optimization metrics interval, so how frequently to fetch the metrics. So if we have observed that to fetch the metrics, right, because if more instances are there, it might take more time to get the metrics. So it might take like 5 seconds or so. But if you are getting requests more like more than 100 in a second or something, fetching a metric every time is not a good option. So we are creating a the frequency of 1 minute or 30 seconds, you can say. And within that interval only it will fetch the metric from the metric system. So this is what is the load balancer is. So based on this, it will take the take care of load balancing and redistributing the incoming requests. So next, load balancer autoscaler. What this policy does is, let me just open the code. So autoscaler defines the condition under which the block instances should be scaled up or down. So load balancer, it chooses the instance, but who is responsible for creating new instances or downing the new created instances is the autoscaler. Can include rules based on resource utilization, request rates, pending tasks, etc. Let's say, just to give an example, scale up when average queue length is more than 100 for 5 minutes, or a scale down when average queue length is less than 20 for 10 minutes. Don't scale down all instances at once, keep it at least one instance running always. So these kind of the rules, if these are the requirements, then autoscaler is the one guy where you need to write your policies. So let me just go to code. So it will also have similar functions like eval function. In that eval function, we'll be doing some metrics and metrics collection. All those things will be done, and then will be decided based on certain parameters. That parameters only I'm going to explain right now. So queue up threshold. So when to queue length threshold to trigger a scaling up. So this let's say whenever a queue length goes beyond the average, right? So that's the time I need to scale up. So that's what the scale up threshold is. Scale down threshold, queue length threshold to trigger a scale down, removing a instance. So scale up is for adding an instance, scale down is a removing of a instance. Idle time downscale threshold. So time in seconds an instance can be idle before being considered for removal. So how this data is measured is, we have basically whenever a inference has been done in the instance, right? So it will update its time. Okay, this is my last updated time. So with that time, it will try to identify whether this instance is doing any job or not for past some X seconds or so. So if it is not doing any job, right, so it means not much of hits are there. So basically the load balancer is the guy which is doing the load balancing and redistributing, right? So if not much of hits are there, requests are there, so slowly the instances may not be in a processing mode. So since they are not processing, they are not updating their timestamp. So because of that, idle time is taken. If they are idle for some X amount of time, downing will be done. Next, instances limit. So how many minimum replicas should be available, how many maximum replicas should be allowed. So it all depends on the your hardware requirement and your costing comes into picture. And timing and averaging. So averaging period, again similar to load balancer, 1 minute average or 5 minute average should be chosen. A cooldown second. So let's say as soon as you created one upscale or a downscale, right, within how many second upscale or downscale should happen. That's what the cooling down is. You should not be keeping very low also, or else for every small burst it can create instances, or it can bring down the instances. So you need to give a good cooling down seconds. Allow downscale with the jobs. So let's say one instance is not having much uh, task now, and it got well, just before saying, okay, this instance is not good. So it has to check whether any jobs are there with that particular instance or not. Basically, it has to measure the queue length again, or check whether that instance is doing any activity, or whether it has updated its metric or not. So you need to check those, then only you need to take a call, or else what happens is the job will be simply dropped. So a load down scale with jobs, by default it is false. Never scale down instances with pending jobs. So this is the this again, I'll explain in my allocation JSON. So I'll not explain the code again. So this health check policy I have explained already in the previous video, where in that video we were showing how to do the identify the whether the instance is healthy or not. So there are certain parameters like failure threshold, number of failed health checks before making an instance as a reassignment, check interval second, how frequently you want to check the this intervals, and gateway URL, because the health policy will do a curl request to the that particular instance to do a reassignment. So you need to provide the gateway URL. So all this data, some very few minor parameters it is taking. So I'm not added again a separate Jupyter notebook for it. So it defines health check mechanism for a block instances, can include rules before determining the health status of an instance, can call a reassignment of an instance to other nodes if the instance is marked as unhealthy. So it could be instances unhealthy, it could be the block itself can be unhealthy. Let's say the instance is healthy, but because of some reason the block is not starting properly, or because of some reasons anything can happen, right? So let's say it was running fine, but suddenly maybe let's say you have copied something to the node, or because of that node becomes unstable, or a instance could be because unstable. In such cases it will identify that, and it will mark that instance as unhealthy, and gives a reassignment call. So that is the health check policy. So now like we have seen all the four policies that is being used during the block scaling and the load testing. When we are load testing, right, so we'll have some strategy with us. So what is the strategy is what we'll now we'll be discussing. That load testing strategy. So load testing is a process of simulating real world usage scenarios to evaluate the performance and scalability of a block. We used a custom script to generate the loads on the block and monitor its performance. So that what is that script we'll be talking in later stage. And the load testing strategy includes the following steps. First, you need to understand is what is your model, what is its limitation, what is its capabilities. So that details you need to have first. So you run your the container image of a model and identify those in a practical hardware that you are going to deploy, let's say A100 or L4 or some H100, right? So you need to identify what is its FPS, what is its throughput, tokens per second. It details how much RAM it consumes, whether you are running in FP16 or Int8, so how much RAM it might consume. All those details you need to have it. So evaluate the model size, disk, RAM, CPU, GPU requirement, tokens limits, or latency or throughput. All those details you need to have it in hand. So for that you need to get these details. Let's say right now I'll be demoing the content of our previous run of Mistral AI Magistral Small 2506, which was running with FP16. It has having a 23 billion parameters. Disk space it needed was 45 to 46 GB because of the model size, and GPU RAM it needed was 45 to 47 GB. Max token it can generate is this much. Latency we have observed for 256 token with a batch of 4, right? So it was taking like from 9 to 14 seconds. So understanding the library. So once we understood the model's limitations, right, we need to understand the libraries. Why library understanding is required is whether batching is possible or not. So certain libraries may not be able to provide you a good batching support. Model splitting. So model splitting is possible or not, and what sort of splittings are possible, like tensor parallelism, pipeline parallelism. There is something known as data parallelism, which is basically scaling. That's what we are doing here. And the library supports those the capabilities or not is what you need to understand from your library that you are using. So in our case we'll be using VLM library because batching good batching support is available. And Mistral AI Magistral 2506 is our model. Batching is supported. Model splitting, yes. Tensor parallelism is what we'll be using. Currently in our testing, batch size that we are using is 4. So define the load testing scenario. So right now in our current example the script we have, right, so we have something as crowd and as well as user. So crowd is like basically how many users to create per hour on a hourly basis. Let's say You can vary that. You can give a configuration like from morning to evening, every 1 hour my user has to change like this, or every 15 minutes user has to change like this. So certain configurations you can provide. So right now number of users 100 is what we have kept in our configuration. And user behavior. So user behavior is like how many sessions the user has to create. Session is basically like chat IDs. Like you will, let's say you are creating new chat interfaces, right? Whenever you are going to a chat GPT or a Gemini, you are creating a new chat interface. That we call it as a session. So how many sessions a single user is allowed to do? 2 sessions is what we have kept in configuration. And request rate per session. So this is this you can get it from our config.yaml. So here I would have provided usage patterns. So like around in the morning time, it has to be 97% of total request. How to calculate total request? So the total request is you need to identify sessions per block and requested hour per session. Basically, in one session, 36 requests can happen in 1 hour. And since 2 sessions are there, totally 36 into 2, 72 requests will go from one user. And how many such users are there? As I told, like there are 100 users, so it's basically 72 into 100. 7,200 is the number of user requests that will go to the block within 1 hour. So that's what you will get the maximum number. And if you want to, if you are not happy with sending 7,200, if you want to simulate a behavior of a low the request coming into your block, right? So you can give a percentage here, let's say 83%, maybe boils down to maybe 6,500 or maybe something like that. So I'm giving a different weightage here, where you can see, right? So 97,000, which is like 7,000 actually. So 7,000 requests will be there around like few hours. Then maybe 6,000 requests will be for few continuous hours. So this way I'm varying it. So you can take your you can vary these numbers according to your node. And there's a request timeout, which is basically to say if request is not served within the seconds, right? So we'll get a timeout, and my we'll call it as a failure. And still it will retry, it will do a reattempt as well. So that is not though it does a reattempt, I will not mark, okay, this though request which has timed out, right, it has reattempt, but I will not mark it. But we are doing a reattempt as well. So these are the user crowd behavior, and what all other things are there in the YAML. Also you can basically check it. Crowd pattern also, right now you can simulate it. Right now I'm keeping everywhere it as 111, and at any given point of time there should not be any 1,000 users, because let's say at this time you have given 1, let's say at this time you have bought zero 0.5, then here the number of users will be 100, and here the number of users will be 50, right? You need to bring down those users. So and again after that, again if you keep 1, right, again 150 more users has to be created. So at any given point of time you are just trying to control, like there should not be any 1,000 users. And user spawn interval, every 1 second you need to sleep before new users are created. So that's what this user spawn interval is. And certain databases, right now we are using timescale db to update our any data entry, right, like input output request timeouts and all. If I want to log it, I am using a timescale db. You can you have to maybe handle the code to handle for a different dbs. So I'm using a timescale db, enable stats, I'm updating the statistics every now and then. And also request response, I'm not using this timescale db, I'm using a different approach to dump my request response times. So this, what is the stats, is basically like cumulative stat and a periodic stat. So cumulative is like from start of the testing, what how much of request has been sent, how much got a success, all those details will be there in the statistics. As well as in periodic stat, it will be like a, let's say a 60-second period, how much request has been sent, how much request you got a success, all those details will be available in the statistics. Then is a logging, certain logging. I'm using a Kolkata timestamp, and load testing log is the file that you can monitor the what's going on. This is a file, log file, which you can log it and check how many requests has been sent. Whatever the stats I'm dumping here, it will also be printed in this particular log file. Then test configuration, duration hours, how long you want to run this test. Let's say 60 hours I want to run, so you can vary these numbers. Warm up minutes, those are like some parameters. So health check interval, every once in 60 seconds check whether those users are healthy or not. That's what this health check interval is. stats log interval. This is 60 seconds. So basically 60 second, every 60 second I'll be logging the statistics into the DB. And this is DMA. So this is something else. So what this basically is, right now, to log this data, right, I'm using one of the ledger service from our AIOS. We call it as a DMA task, a DMA ledger service, which basically it's a request call. I'm not doing a, I'm not dumping this, I'm not using this anywhere, I'm using this for something else. But to that request endpoint, right, I'm sending, whenever I get a response from every request, I'm just dumping that data to the DMA endpoint, which is a ledger service, which just records the data into the timescale DB. Again, I'm not directly interfacing with the timescale DB, but I'm using some service available within AIOS, which is called it as DMA ledger service. So so this is about the defining a load testing scenario. Next, understand your hardware. So initially I gave some number like 7,200, right? So what is the reason that I came up with that number is what I'm going to explain here. So before doing that, you need to understand hardware available with respect to the model requirement. So let's say this is our model. What all hardwares are available? First, you need to note down those numbers. Let's say I have these are my hardwares available under for testing. I have one A100 with 80 GB GPU with 12 GB CPUs, 12 vCPUs, and there is Node 2 which is having a 2 into 100 A100. Two GPU cards are there with 80 GB each, 24 vCPUs. Again, I have four L4s, 92 GB, because 23 GB each I'll get from each L4. So into 4 is 92 GB. So, and again I have one more Node 7 which has 2 into A100 cards, again 160 GB, 80 GB from each. And we have a 4 A100 as well, 320 GB, where 80 GB each with 48 vCPUs. This is my nodes available for my load testing. So now let's calculate how many instances of my model can run in the these nodes. So one instance takes around 47 GB. That's what I have measured for this particular model in FP16, right? It was taking around 47, 45, 46 to 47 GB of RAM. So only one instance can be run in A100 because it has a 80 GB, only 80 minus 47, 33. So second model, I cannot put it here. And three instances can be run on two A100s. Why? One instance of this Magistral model I can run in each A100. Again, that 33 GB, 34 GB is available, right? I can do a sharing of GPU, or I'll say model splitting I can do by splitting the model in those two GPUs, and I'll be using tensor parallelism. And now tensor parallelism number is 2, basically because we have two GPUs. Or in one instance of 4L4, right, which is having 92 GB, I can run, since 4L4s are there, I can run around 47 GB, which is only one model I can run. Other 47 plus 47 is 94, so I cannot run the second model here. Only one model I can run in 4L4s. So we have observed that the throughput, there is an issue with it when you are doing a tensor parallelism or things like that, right? So we are seeing some discrepancies in the throughput. So that's what I'm going to discuss now. For this particular model, I'm specific to this particular model. It might behavior might be different for different models, but in this in our case, this model, when one instance of A100 is run, it was when it was running in A100, right? Only one instance, which was occupying 45 to 47 GB. So it was taking 30 to 31 tokens per second is the generation tokens. So not evaluating, prompt eval is not prompt eval, it is the generation, output token generation, with a latency of 14 to 15 seconds. So for 256 tokens when batched with 4 requests. So in our test we were batching it because we wanted to get a bigger throughput. So we were doing a batching operation because VLM supports batching, and the max tokens that we wanted to generate is a 256 tokens. So 256 into 4 requests will be sent parallelly. So during this testing, we observed that 30 to 31 tokens will be getting it within a time span of 14 to 15 seconds. So effectively, that downs to like 60 to 62 tokens for two GPU system. Like we have two A100s, and for a batch of since I'm going to run two instances, right? I'll get around 60 to 62 tokens from each two GPUs. But since batch size is 4, I have to multiply that number as well. So basically at the end it will be like 242 to 48 tokens per second from both the GPUs. This is what my tokens per second for this particular model in 2 GPUs with 3 instances on 2 A100. So this is very important. Like right earlier, this was the number for 2 instances in 2 GPUs, but right now I'm calculating 3 instances on 2 A100 same cards. So the effective tokens per second was coming down to 14 to 15, meaning 14 to 15 tokens are generated per second from each instance. Total 3 instances are there, but they are distributed in 2 GPUs. One instance is completely running on one GPU, other instance is completely running on other GPU, whereas the third instance is sharing the splitting the model as a tensor parallelism equal to 2, and it is splitted and it's running in the both the GPUs. In such cases, the utility was the tokens per second was coming down. So if you calculate effective tokens, right? So basically 3 instances were there. So 14 into 3 is 42 and 15 into 3 is 40. So 42 to 45 tokens per second I was generating. And since it is batch size is 4, if I multiply by that, so I'll get a lesser tokens per second. It may not be the case for a smaller models. Smaller models might quickly start and quickly end, right? So in that case, we might by simply splitting 3 instances in A100, we may not see this kind of behavior. But for this model alone, I am discussing. So why tokens per second is reduced is basically the GPU utility. So just to give some screenshots, I have noted down. So this is when 4 instances are running in 4 A100. So 96, 96, 96. This was maybe just starting at that time. This utility was seen like it was ranging from 96 to 100, 96 to 100. But when I added one more instance where splitting was happening, right? So as you can see, there is a 24 GB and 24 GB. Basically, this is the instance which was getting splitted in these two GPU IDs. So at that time, if you see that GPU ID is 1 and 3, it was on a continuously 99 to 100% that GPU. So it means like it's because of the utility, not any other reasons. So utility was not sufficient enough for the model. So that's why the whole because it has to do a lot of scheduling and all, right. So there is a streaming multiprocessor. The kernels has to be scheduled properly in the streaming multiprocessor. There will be time that they will take some time to schedule. All those things will happen under the hood. So because of that, the utility was of the GPU was also going high because of it has to do a lot of tasks now. It's a big model. It has to do a lot of tasks. So utility was always 99 to 100. So that's why the tokens per second on an at the end, right, it was coming down. And when I put a four instances, right, four instances on this A100, it was like almost all are like 6 instances. When I put deploy 6 instances, because 4 instances each, and then 2 more instances were sharing two GPUs. At that time, it was seen that it was almost like 199, 199. So this is the reason we were getting a lesser tokens per second. But still, we wanted to test how more number of instances will behave with AIOS. So that's why we were going ahead with sharing. So you can avoid also to get a higher tokens per second. The sharing you could have avoided, but again it is on a per basis, model basis. Like you need to understand your model, then only you need to take that call. But in our case, we want to test more instances. So with available hardware we have, that's why we were allowing the sharing. So let us see how many instances we will be able to create. So on node 1, which is having only one A100, so only one instance I can create. Node 2 was having two A100s, and node 7 was also having two instances of A100, sorry, two A100 cards. So that's why I was able to run 3 instances. And in node 4, there is only one, 4 L4s were there, only I was able to run one instance. And there was node 9 with 4 A100 cards, so I was able to run 6 instances. So summing up, we will get a 14 instances. So let's calculate the effective throughput of that can be achieved on an ideal case. So from one instance where it was batch size is 4, only one instance, and 30 to 31 tokens per second we used to get, right? So if I multiply them, I'll get 120 to 124 tokens per second from the one instance of A100 and one instance of model in the one GPU. If I have node 2 which has two GPUs with three instances, batch size is 4, and my effective token is 14 to 15 seconds. So this was the tokens per second. Similarly, I was doing this for other guys as well, node 4 and node 3 as well. I was trying to do. So the numbers that we were getting is around 864 to 920 tokens per second. I was getting it. So now let's say then how much request is honored in this tokens per second is basically I need to divide that 256 tokens request that can be handled per second, which is basically 3 to 3.5, 3.3 to 3.5 requests per second is effectively achieved. So just to keep this number little below because it's an ideal cases, right? So when something any other delays can happen in between. So I'm just keeping my request per second is 2 requests, so that is nothing but 2 requests into 2 requests per second into 36,000 seconds. That's why the 7,200 requests we are getting. So even if you increase by let's say 3, so you will see a little bit of higher maybe your latency can increase a bit, so that queue length can go on a higher side, so that's possible. So basically we are keeping this number into our testing case. So yeah, so this is about the understanding hardware available with respect to the model requirement. Next is about logging and monitoring. So log the request response time, errors, and other relevant metrics to DB. So so that we can access those data at any given point of time, because this test will run for hours together, we need to have those data backed up somewhere. So we'll be using timescale DB to store the metrics, and I'll be using a DMA endpoint to hit those data to dump those data to the timescale DB, and custom scripts to visualize the above metrics, because either you can dump this like you can integrate with Prometheus as well, but I'm using a custom script because my data is in timescale DB. And monitor the resource utilization and metrics of the block instances. So block will also provide some metrics for us to understand, so that also I can use it. So next, monitor the block performance during the load test, check the latency, error rates, queue length. So these things we will be I'll be showcasing to you. So this is about the theory part. So let's get started with the, I'll not be running the activity directly, but I'll show you how to do that. So this is the main thing where it will initiate certain env variables for this Python to run. So you can simply run this cell. So once the cell is run, right, so you have a for resource allocation policy, the code is already I have shown you what are the parameters. Also I have shown you need to register those components, how to register, how to unregister, and how to upload the zip file. Everything is mentioned here. Similarly, for a load balance, it is also mentioned here. Register it, then if you have done any modifications, you can unregister it and register again, and upload. Anytime you modify the code, right, you have to zip it and you need to upload that. So once uploading is done, so that file will be the AIOS instance can take those files, and wherever these files are uploaded will be mentioned again in the registration JSON file, right, whatever the register.sh you have here, those where this files will be uploaded is mentioned here, and AIOS system can, so that AIOS system can pull those zip file and unzip it and run the function.py you have, and upload this file. Yeah, it's for auto scaling, and similarly for a health check policy. So now, yeah, once this is for the policy. Now how about a block? So I'll be showing you the block code. Yes, so this is the model code we have. So here one main thing is this, like the build a docker it was for llama cpp version of the same code. It's for the llama cpp docker image, and this is for a vllm building docker. So you can run build docker vllm bash. So it will build the, if you take this content, it will build the docker that is needed for this particular test. And what all the important files are, main orig vllm batch is there, right? So that is the file, that docker file will basically, this docker bash file will be running this docker file. It will use this particular docker file vllm, and in that you can see that it will be using the main orig vllm batch, and certain other files it will also be using. There is a library vllm batch, right? So this library is used by llama cpp. This library vllm batch is used by vllm batching. So I would have just commented certain lines here, maybe in the init. Yes, so the library import llama util set, right? So that I have commented here. So maybe if you are running a yeah, if you want to run the llama cpp, you need to enable this. If you want vllm, you need to enable this. So for time being, it's a vllm, right? So I have enabled only this. I have commented this. That is the only change. You need to modify to compare the llama cpp and vllm. Why I am not choosing llama cpp? There was no way to for me to use the using Python version of llama cpp. I was not able to do a batching, so batching was needed for me. So that's what I ditched the llama cpp and I use the vllm library. Yeah, sorry, I'll show the code. Yes, so this main orig is what the main file of the llama cpp. Basically, it has it has this VLM chat application where it creates the instance here somewhere. It is similar to the Llama CPP code only, but only thing is a little bit of changes happens in uh, the VLM util code, where earlier it was Llama CPP, but it is VLM, right? So how to load the model in the VLM? VLM does a lot of optimizations like KV cache optimizations and all, right? While doing a KV cache optimization, it will try to take entire GPU. So we have put some controls, how much GPU it has to select, whether it can do FP16, int8, all those kind of controls. We were doing it in our Python version of code. So that's why you have to take a look of the not this is just the interfacing only, but actual heavy lifting will happen in the VLLM batch. So here's small functions are there you can understand. Get valid TP. So TP is tensor parallelism. If let's say the container, whenever it is running, it has 2 GPUs, it will identify those GPUs and identifies how much of tensor parallelism it has to do. Let's say by mistake you apply 3 GPUs to the container, still it has to choose only 2 GPUs, right? So this function will take care of that. Best FP8 D type. So there were several D types available. D types were available in the Llama VLLM. So for what version of hardware, which one to choose, certain configurations we have provided here. And estimate KV cache byte. So by default it will take entire GPU. VLLM will take entire GPU because it want to give the best throughput. So that's why it is taking entire GPU. So but when you are in a shared environment where not just one model, you want to deploy multiple models, right? So in such cases you have to have a good control. So for that you have to estimate the KV cache size requirement. So that's what some matrix multiplication is going on here to calculate that amount of KV cache required. A minimum amount of KV cache required will be selected here, and number of GPU selection, detection, memory detection, or free bytes available. So those things are taken in this particular file, and it will calculate how to deploy the VLLM model effectively. At the end, it's a VLLM's API only will be using for loading the model. So you have a load model is here, and you are trying to load the model with the config you have, and LLM model you have to provide the path and model config. And model download will happen in this main origin only. So model downloading will happen, and this model will be available in one particular place in that the node. So even if second instance starts in the same node, right, it will reuse that, it will not re-download again. So that's what this function will take care of, downloading it in one particular place so that model can be reshared. So the static files of the model will not be downloaded again, it will be reshared. So this is the block code. Right now in that block code, right, only generate interface has been added, no chat interface has been added because of batching requirement. I had to use the generate interface, not the chat interface. So so you have to build the build docker vlm.sh, then push the docker to the registry you have, then register the component, and register the component is available here, and deploy the block. So before deploying the block, one thing you need to have importantly is the allocation file. So let me go to the block. So this is the model code. These are policies you have, right? So all the 3-4 policies we have seen is available here, and the block. So here Magistral VLLM is what you need to choose. If you go to the allocation, so yeah, this is the block ID that I'm going to create. Next, init data, the model name is Magistral 2506. Basically this model is same as a Hugging Face model name. So basically we'll pull that file, and we'll be doing the downloading those all the safe tensor files from the Hugging Face. And the important thing for me to showcase is this guy, the policy rules, right? So what all policies are available. The cluster allocator, basically it is identifying. I have given a hard-coded cluster allocate here, so you don't have to do query like what all clusters are available. This kind of query is not required, so I'm directly hard coding the one cluster I have. So this is the cluster allocation. Next is a resource allocation. For resource allocation, what all parameters are there? So minimum CPU per instance, I given 5. Minimum memory per instance. This is for the resource allocation. So this will define the what is the minimum required RAM, CPU, GPU, storage, and all. So these are the parameters, and these are the parameters that I want to take care of while finalizing the node. So if they are 80% occupied, right, 80% occupied, or 80% memory is utilized, or 80% vCPU is utilized. So I'll not be choosing that particular node. So this is what, and also the weights, so how the weight should be. Next is load balancer. So in the load balancer, certain parameters are there which I have already discussed: average period, tiebreaker, redistribution percentage. So those parameters are here. So this is for the load balancer. And similarly, this is for stability checker. It doesn't have too much of parameters, only failure threshold. 10 times it will monitor if the instance is found to be failing for 10 times with an check interval of 120. 120 into 10 is basically like what, 1200 seconds, right? So basically 20 minutes. So if for 20 minutes you can reduce this, there is no harm in reducing this. If 20 minutes model is not under good health, so we'll be doing a redistribution, sorry, reassignment. And this guy is the autoscaler. The parameters I discussed earlier already. So this is the parameters of the autoscaler, where idle time downscale, like only when 10 minutes, if one instance is not received, then delete it. Don't delete the instance if it has some jobs. So cooldown, every 5 minutes once you can do upscale or downscale, which is like 300 seconds. So maximum replicas, minimum keep one instance, and maximum replicas reach only 14 instance, not beyond that. And Q down threshold. So on an average, if Q is less than 20, right? So then we can think of a starting of a down scaling. So that's what this Q down is. Q up is if the average Q length is beyond 100, right, of any instance, then we need to think of a allocating an instance. So that's what this parameter says. So this is the autoscaler. So once you modify those values, or if you imagine you have changed the policy to cater your requirement or require your need, so you need to re-register those policies whenever you done a code modification, upload the zip file, and again restart the block. You kill the block and restart the block, so that it will take the latest policy files. Or there are certain policies like load balancer, right? It is an continuous process, so it will never kill itself. It will be available all the time, because it can get a hit anytime, and it has to decide where to do a allocation. I mean, where to route the incoming request. Whereas auto scaling and all, they will run once in a while. So once when they are running only, they will pull the zip file. So if you are done a modification only to the auto scaler, you don't really have to restart the block. But only for load balancer, you have to restart the block. Other guys, they will run once in a while. So they will, if you upload the zip, that's enough. It will take the latest zip and it will do the processing. So once block is created, deploy the block, and you want to get the details of a block, right? You can call this endpoint and it will give you the details of the block, where it is deployed, all those, like whatever the registration you have done and whatever the parameters you have set to the policy, right? Those will be, you will get it. And to do the inference, you require an inference server. So I would have already spoken how to deploy this inference server. I have provided already some files. So you need to run this to create an inference server. So the inference server, via inference server only, will be basically our code. The load testing code will hit the inference server. Inference server will talk to the block, and block will respond back to the inference server, and the inference server send the information back to our client code. So this is an generic inference request looks like. And to get the block matrix, you can use this endpoint block Magistral 2506. So this we can put it in the browser as well. You can really get a big JSONs. So whenever the block is running, right, it will give how many instances are there, what all different metrics it is noting down. All those details you will get it. Let me try to run this just to see. Yeah, we are getting some metrics. So there is an executor. This executor is basically the load balancer. So this instance ID is there, right? It's an executor. This executor is basically the load balancer. The whatever the policy you have given for load balancer, it will be doing it, right? So for that also we have a metrics here, like how long it's up, how many tasks it has processed. Those kind of details are available here. And this is the actual instance. One instance is available right now because no task I'm giving. So it has having some content in it, like a lot of details that you can go through one by one, related to the model's metric. So now to remove the block, once the task is done, you can remove the block using this command. So you need to just pass the what is the model you want to delete, and what is the cluster. Right now I given maybe a wrong cluster name, but yeah, what is the cluster you want to remove it. Then so that's for the creating the block. Now next is a evaluating the response time and failure visualization code. So since I told like we'll be my our script will dump those data to something known as DMA. DMA is one unit in our AIOS system where it acts like a ledger. So whatever you dump it, it will be put it into the timescale DB and you can later on retrieve it. So so to enable those, right, so you need to run some environment variable. So in this environment variable, this sh file, you just add your the informations like passwords and all. You can just put it here. Questions, yeah. So this is the environment file, so you can dump your data here. Yes, so you can give whatever the details you want, right? So you just dump it, so that will set into the environment, and then run this bash file. So you can run this bash file in a screen command, so that it will be always available for you to check those. Basically we'll be using Streamlit here to query the timescale DB's content and display as a graph. Just to give an example here, this was my command. That's what I have opened up here. So the content of that will be use the test ID. So you need to, like, whenever my script runs, my simulation script runs, it will create a test ID for you, because you can control C and again start a test, right? So test several times you will be changing your configuration. So just to make sure you know one configuration that you are going for a bigger test, so that test ID you can take it and you can put it in the left side filters here. So you can choose the date time, and averaging 60 seconds will happen here, like average across 60 seconds it will collect the data and it will average and it will give you some details here. You give the test ID and submit it, you will get the details like this. So let me just try that, because it might take some time. Yeah, so because it has to fetch a lot of data, so it might take some time. This the like you will get what you will get in this UI is average response time within a 60-second averaging. So wherever you are seeing a very high number rate, basically those are the failures. So so you are seeing a response time varying from, let's say, on an average like 100 to maybe a 400, 500. It is varying continuously and going down as well. So because of the pattern that we have given, request of pattern we have given. So next is a, just control this. Okay, next is a request count over time, and the request count over time is basically how many requests it has been processing. So it is around uh, it's a 4K, I guess. So it is a 60K, but I have, like, let me just get the data. So it might be like around 300K requests has been created. So it is maybe the old data screenshots I have. And also next is a failed request in first attempt, meaning like how many requests has been failed. Maybe around at 60K it was this number, around 145 maybe. But when we checked for 300K requests, right, it was just some 700 requests has been failed. The failure will make sure that those failures numbers can be reduced by tweaking certain components here and there, so that will take care of it. So but that's the number. So let me, it is still going on, so let's wait. So next is a Grafana dashboard. So this we have a tightly integrated all our metrics to the Grafana, the Prometheus Grafana combination. So first of all, you need to, let's say if you have a new Grafana created, you need to configure the data source. Right now it is Prometheus, and this is the URL you need to provide. So since you are in a AIOS cluster, right, so it will take care of changing this to proper IP and all. And once a data source is added, then you need to create import the JSON file available in this particular yeah, the dashboard JSON. So this you need to import in your Grafana. So I prefer having latest Grafana, because certain things may not be available in the older versions of Grafana. So so you import that JSON, and you can just before importing, you just have to change your source ID. Source ID, like when you onboarded the source ID, it will generate on UID. So that UID you need to change in your the JSON files. So let me just show you the JSON file. Yes, so time panels. In the panels, you might see some data sources, there you need to change it. Let me just check it. Yeah, the data source, right? So the UID, so whatever the UID you will get, you have to update it and then upload the JSON file to the Grafana dashboard. So it will get a visualization like this. So that, let me just show you here the live dashboard. So what all are available here? Load balancer, queue length, load balancer latency, because the load balancer is very fast. So only for a few seconds, it might take 1 second, but most of the time it is like very minute. So 0.0393. So it will be very quick in its activity. End-to-end total count per instances. Let's say here the graph is breaking, right? The reason is um, it could have downscaled now. So that's what you will see, a graph and sudden vanishing. So again, once the downscale happens, again, if more requests are coming, again it will upscale. So that's why you will see several graphs here. This is the end-to-end count total per instance, like how much request each and every instance has processed. That's what this number is. So aggregating those numbers are here. Queue length average 1 minute per instance. So what are the queue lengths on an average? So this is for there for every instances, but if you require averaging, right? So it is here basically. So on maximum of 1500, 1200 queue, 1600 queue has been reached at one point of time, but later on it is very less only. It's like 1000, 1000, 1000. So if you, instead of 7000, if you start like 8000 or 9000, right? So you might see this number little bit increased. That's an average queue length. So this is inference empty tokens. So empty tokens is basically, we have seen that in VLM library when you're doing batched inferences, sometime the VLM responds with an empty token. There will not be any output at all. So we are just noting it down. So that's why I've given this graph as well. End-to-end latency. So on an average, as I was mentioning, right? So you will, when 14 to 15 tokens per second is received, that means in a two GPUs there are 3 instances. So that is this interval. And if you are seeing a 30 seconds, which is basically sorry, the 30-second, it's a latency, right? So if it is 30-second, it means three instances in a two GPUs are available. If it is 14-second, it means only one instance are present in one GPU. So that's why you are seeing two different graphs here. One is at 31 seconds and one is at 50 seconds. So here you have LM tokens per second. So tokens per second, again you will get 14 to 15 tokens per second also you might see, or 30 tokens per second also you might see. Sometime you will get a 50 tokens also. This is a very rare cases. And this is the instance count. Wherever instances are going up and down, so you will see that numbers here. So whenever response, I mean more hits started coming, instance will go up, again it will come down. So minimum of one instance will be there available all the time. So right now the test is not running, so that's why you are not seeing any further content here. So on process latency, what is this on process? This is the main heavy lifter guy in our instance code. So that's where the batching and inference will happen. So batching here is very straightforward batching. Like say, I'll just show you the code for a batching. So in the main.py we have on process, on pre-process. Yes, so this is the main function where whenever a request comes, right? So it will, the first it will call this particular function, and in this function we have something known as batcher. What this batcher does is it is now right now only the simply batching the number of configured let's say you have configured batches as 4. So only when it reaches the 4, it will allow the next things to go, or else it will simply continue. So in our AIOS code, we have handled that. If it is if it is not returning anything, it means batching is still going on. So AIOS will not respond back to the immediately to the inference server. So it will also hold its inference request result. So once batch is done, then only it will do the actual inference here. So we right now it is a very simple batching, but you can also utilize, like sometime we have seen, let's say user request is sent once, and right now the batch is 0. I mean, there's nothing in the batching, this particular key, this particular variable. There is no data here, and user has sent one request, and one batch is now 1, but it will not do inference because it has to reach the batch size of 4. It's because of, again, the stricter requirement of the VLLM. If you are saying to VLLM that I'll send 4 requests, we have to send 4 requests, or else the anything can happen to the library level, it can fail. So that's why this batcher will wait for the 4 requests to come. But if your library supports no, though that's the maximum, you can send 1 also, you can send 2 also, in such is the case, right? So you have to modify this a bit to handle the timestamp as well also into consideration, not just the batch size. Batch size is one. If batch size is met first, then it will return the batch. If time is met first, let's say give a 1 second as a wait, or a 5 second as a wait. Within a 5 second, whatever data is there, right, that is the batch now, and it will be sent. Whether it's 1, it's whether 2, it doesn't matter, it will send to the batch. That way also you can modify this batcher here. Batcher is very simple code right now, but right now I have not done that. The reason being is I'm depending on the library that I use. So yeah, so this is the on pre-process latency. So on an average, it will be 14 to 15 seconds when only one instance is available in A100, but it will changes to 30 seconds when 2 instances are there in A100. I mean 3 instances of in on 2 A100s are there. Then we'll get a 30-second latency. So this is total tokens generated. Total token generated from each instance is available here. This is on preprocess count total. Yeah, how many requests are processed in on preprocess function is given here. So similarly, you can add more and more the metrics you want to monitor. Just to give an example, let me just take this. Yes, so you have so many details, right? Not just that FPS, end-to-end FPS, end-to-end latency, all those details you can put it into VLLM just by creating a new panel there. Right now, whatever is needed for us to understand, so that much only I have kept it here. But you have several parameters here, several CPU utilization of the LLM model, GPU utilization of LLM model. So those details, if you want to monitor, right? So you have those details here that you can take it and put it into the dashboard. So as this is very huge data, might be it's just taking time. Okay, so now Grafana is done, our Streamlit UI is also done. So let me just how to run the crowd simulation code right now. So we have a crowd.py and user.py, 2 files are there, and the crowd.py file contains the code to simulate the crowd behavior. To fetch, first of all, you need to query to the LLM. Right now, to query to the LLM, you need to have some questions, right? So first we need to collect those questions. How to collect those questions is we have a generate questions.py. This uses the Gemini API to fetch some random questions. You can give the details like what all the subjects you are interested in, maybe science, sports, or any general math or something like that. You can give the details in this particular file, and you have to provide the Gemini API key as well. So it will generate some random questions for you. So right now I have already question.jsnl file which has around 4.9k questions. So these questions I'll be using to every user, whenever they create one request, they will randomly choosing these questions, and in the randomness, we just want to make sure that randomness is available, that not from the starting one. The reason being is let's say once if it is not randomness, if user selects or user 1 selects first question, user 2 also can select the first question. What if it goes to same instance? During that time, the caching will take into picture, like okay, we have a cache will be stored by the LLM model, so it will return the tokens from the cache. I don't want that to happen, so that's why we are out of 4.9k questions, I'm randomizing it. So now each session IDs will pick the questions from there, and once all the questions are over, 4.9k all questions are over, again it will try refreshing the keys, again questions from that file, and it will again randomly it will choose the questions. So you have to install certain dependencies, requirement.txt, requirement.streamlit.txt. You need to this is for running the Streamlit code, and this is for our main crowd.py code, and you have to set the environment variables also, because timescale.db is used, right? And so then you have to run the crow.py. So one other main file is a conf.yaml. So modify the conf.yaml that is suitable for you for test scenarios. So modify that file and run the python crow.py. Better to run this in a screen, because it will run for 60 hours or 80 hours or whatever the hours you want to run. So so that when you close your work, so it should not get killed. So you run it in a screen command, or make it as a daemon. uh, so next, user.py. So this crowd.py will just talk about creating the crowd, like basically creating the people, and user.py has the control over how to distribute, how to create the requests, how periodically to create the request, how many requests to create. Again, it will read the content from the config.yaml file, and it will generate the simulate the user's requests. So upon each request, like whenever a request has been done, right, you will get a response from the inference server, and that will be recorded in our timescale.db with this content. Basically, we have block id, session id, sequence number, type, whether it's success or failure. Failure happens whenever your timeout, like 1200 seconds timeout occurs, right? You will get a failure. And response time will be put raw data. Right now we are not putting it. Test id, user id, start time, end time, your start time obj and end time obj in str. So it will be converted to str basically at the end. So those details will be available in the timescale.db, so that my Streamlit code will fetch this and to generate the average latencies, and average latencies, total number of requests processed, or average failure. Like if it is a failed, right, type is failed, so it will count this data. So maybe it's taking more time. Am I giving the right times? Okay, let me just, okay, so let us see in some more time. So it divides, so basically what this user.py does is it divides the user request equivalent equidistance, meaning, like, let's say you have 7,000 requests to be generated. Let's break that 7,000 to 36 requests. For single user, it is 36 requests per session, right? So 36 requests divided by 3,600, I mean 3,600 seconds divided by 36 is nothing but 100 seconds. So every 100 second, one request will be sent from one session of a user. So since two sessions are there, so two requests will go every 100 second. So at the end of, like, 0 second, 0 second, there will be two requests from one session, and 100 second there will be two more requests from I mean both the sessions will be there from this file. So once you run it, you will tend to get the data like what I'm showing here. So that's about this Jupyter notebook. So you can run this test at your, but before running the test for your model and your available hardware, right, you need to calculate those. So don't forget to calculate those details. Yes, I got the response time analysis, where it is showing you the response time series visualization. The response time is varying from 0 to 800 seconds. On an average, it is like data is available within like 50 to let's say 600 seconds. This is for the response time, and you can, the number of request counts, right? So it has started from like it has gone to like around 320k requests has been served within like in a span of 60 hours of a test that we conducted. And the number of failures is basically timestamp timeout errors. So somewhere it has reached to 722. So this is what we are trying to say, that we'll be handling in our future release. So this is the graph of a Streamlit, which shows you the response time. So that's it for this video. Thanks for watching, and keep supporting us. Thank you.